The following is an AZPM original production.
Arizona Science is supported by Research Corporation for Science Advancement.
For Arizona Public Media, I'm Leslie Tolbert, Regent Professor Emerita in Neuroscience at the University of Arizona, and this is Arizona Science. Our guest today is Euan McLeod, Associate Professor in the university's Wyant College of Optical Sciences. Euan is an expert in nanophotonics and holographic imaging of objects. He uses high-tech methods that allow us to see tiny objects and analyze and understand them. Welcome, Euan. Thank you for joining us.
Thank you very much for the invitation. I'm pleased to be here.
You use what you're calling tunable optical lenses. Tell us how that works.
The idea is to have a lens where you can change the focal length. And so the idea is, let's say there's something really close in front of the lens or something that's really far away. Normally you really want to change the focal length so you can either image that really close object or image that really far away object. A lot of kind of conventional optical systems, the way they do that is they have many different lenses in series, and then they put this on some sort of mechanical device where you can move that lens in and out. So that process is kind of slow because if you have a big heavy lens, you can't move that really, really fast. So one of the things we were interested in doing was building a lens that you could modulate at very high speed.
And so you can use it to look at things as small as viruses.
Right. In our case, we've recently done some projects to diagnostics on things like viruses and proteins and other biomedical things. We're interested in building some kind of small, compact, portable, rapid diagnostic devices for kind of a wide variety of potential diseases. One example was a few years ago during the COVID pandemic, we looked at trying to identify those protein molecules that are on the surface of a COVID virus. These molecules are too small to see directly in a microscope. The best you can do with a normal microscope might be about half the wavelength, or about 250 nanometers. But even then, if you can see like a 250 nanometer spot in your microscope, you don't know if that's a virus or if that's a piece of dust or something else. So a lot of times you want some sort of molecular specificity because we know that, for example, the COVID viruses have certain types of proteins on the coat. And so we want to be able to identify kind of that based on its chemical properties. And so one way you can do that is you have some sort of capture molecule that is going to bind strongly to that specific type of protein. We took these capture molecules and we chemically attached them onto microscopic beads that are about the same size as kind of bacteria, but they're made of plastic. They're made of polystyrene. Those disease molecules are going to bind onto the capture agents, and these beads are all going to kind of cluster together. And if you've seen kind of animations of antibodies grabbing onto things, that kind of happens. But now these beads that are the size of the bacteria, they're easily visible within a kind of a normal microscope system.
And how far along is this?
I would say the kind of research proof of principles have been done. We have some papers published on it, but it's not something that's been kind of transferred into technology that's being widely used yet.
So you also use your lenses for nanofabrication.
Yep.
Tell us about the tiny things that you make.
Right. So that's kind of the other half of the research that we're doing currently. We are using a technique called optical tweezers to essentially 3D print material, but with much smaller resolution and much smaller feature size than other types of 3D printers that are out there. An optical tweezer is essentially like a tractor beam, but it's something that only works at small length scales. So the idea is you take a laser beam of light and you focus it down to a really tiny spot, and the photons in the light, they have momentum. And so if that photon hits something, like a small little plastic bead or a little metal nanoparticle, that object that photon hits is going to scatter the light. And when that happens, it's kind of like, you're throwing, balls at something, and you make that something move a little bit. And so we're basically using a laser beam of light to pick up a particle and stick it somewhere, and then we go pick up another particle and stick it, and we try to do this as fast as possible.
Thank you very much for a really fascinating look into what feels like the future of imaging and the assembly of nanoscale objects that we can hardly imagine. Euan McLeod is a leader in the development and production of high-end tools for imaging and manipulation of materials at the molecular scale. You can listen to this and all Arizona Science conversations at azpm.org/Arizona Science. I'm Leslie Tolbert.
Thank you to Research Corporation for Science Advancement for their support of Arizona Science. AZPM podcasts are made possible in part by donations from listeners like you. Learn more at support.azpm.org. Thank you.